All right. Again, this is called the fundamental theorem of calculus. Section 5.4 is what we're starting today, is the official full presentation of the fundamental theorem of calculus. In 5.3, we used the fundamental theorem. You saw some fundamental theorem questions on the quiz, but they were more on the light side. All right. I've actually presented most of the fundamental theorem to you guys. So there's going to be some new stuff, but a lot of it should be at least conceptually a review. So what was the fundamental theorem? Well, we kind of wrote it down. There's two parts to it, and I'm going to formally introduce that today. But the first part was the one where you took the derivative of an integral. And what did we realize that brought us back to? The derivative of an integral brought us back to the original with x's in it. We need time. The second part is actually finding the area under the function, finding the area between the function and the x-axis. Antiderivative, plug in b, plug in a, subtract, get an answer. It's a number. It's the area. That's it. Okay, that's the short end of it. But then there's these conceptual questions that the AP test writers love to put on there. These will typically come in the form of a free response. Okay, so let's practice the concept. You need to get a couple things straight first. First, what graph are you looking at? G or F? You're looking at F. So what's G? Wayne? The area. G, eyes up here. G, it equals the area under F from 0 to x. So 0 is our reference point. We're starting at 0. Remember that worksheet? Column 1, column 2, column 3? G is the same as what we called A of x, B of x, C of x. Okay, it's that column 2. How would I find G of 1? G of 1 is the integral from 0 to 1 under f of t dt. This somehow it got erased here. This should have a dt here. dt. How do I find the area under f from 0 to 1? Well, it's actually a quarter of a circle. Do you agree? And I should have told you that. They're using the graph of f and the test writers will say something to the effect of evaluate g of 1, where f is a piecewise function broken up into a semicircle and a triangle. Okay, they'll tell you that's a semicircle. So if this is a semicircle, the integral from 0 to 1 would be a quarter circle, which we can find the area geometrically, right? Isn't the full area of a circle pi r squared? So this is a fourth of pi r squared, where our radius is 1. So what's our area? Pi over 4. Very good. A fourth of pi times 1 squared. A fourth of pi. Pi over 4. All right, let's keep moving. What's g of 2? Integral from 0 to 2. Isn't that another pi over 4 added on? What are we up to now? Pi over 2. We're up to pi over 2 now. Are these trick questions? You got Y-ball in the mind? Valentine's dates? Moving on. That was G of 2. G of 2.5. Integral from 0 to 2.5 of f of t dt. Well, wait a minute. What's going on now? G of 2.5 would be this green. This is 2.5 right here. So we have to take pi over 2 and subtract that little triangle area, right? If this is 2 and this is 2.5, what's the whole base of that triangle? Good, a half. What's half the base? A fourth. Times the height, -1. So we're subtracting what area? 1/4. What's g of 3? Integral from 0 to 3 of f of t dt pi over 2 minus a half. A half. Are you guys okay today? Am I confusing you? Okay, good. You're like dead. Ooh, now it's getting spicy. Determine where G has its maximum and minimum values. Ooh, wait a minute. This sounds like a first derivative test, doesn't it? Maximum. Or the maximum. Help me out. G will have a max when G prime of x goes from G prime changes from positive to negative. All right, in case you've been zoning out or slightly or heavily apathetic, okay, for your own good, this is the part you really, 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 really need to listen to, okay? How do I analyze G prime? What's G prime? AKA, like some of the rappers you might know, or even watch on the halftime show. Eminem, AKA some shady, AKA Marshall Mathers. Yeah. We got a lot of names. Do you agree? Just like calculus, these graphs have a lot of AKAs. Are you ready? See that transition there? Pop culture, they really gets the students really ingrained in the lesson, and you bring them in and you teach them the calculus. Teaching 101 right there. Make it cool and hip and exciting. Pitbull. Mr. Worldwide. I don't know his real name. Pitbull's so old. That shouldn't have been. See, I lost a lot of cred there. I feel like all the rappers nowadays have like either Young or Lil in front of them. Young who? Lil. Help me out here. Young Weezy. Is that one of them? Lil Wayne, Lil John, Lil Kim. You guys should just leave me out to dry. Rough crowd. All right. That didn't happen. Here is the moment of truth. If I want to find G prime, if I take the derivative of the left side, if I take the derivative of the left side, I have to take the derivative of the right side. You ready? The derivative of g of x is g prime of x. What is the derivative of the integral from 0 to x of f of t dt? F of x. Very good. Moment of truth. G prime of x equals f of x. Good news for you. If we're looking for where g has a maximum, and I'm looking for where g prime changes from positive to negative, can't I look at where f changes from positive to negative? That's awesome, because we're looking at the graph of f. Where does f change from positive to negative? 10. 2. G has a local maximum at x equals 2 because g prime changed from positive to negative there. Does that make sense? Where does g have a minimum? Does g prime, does f, ever change from negative to positive? No, but what else do we need to look for? Endpoints. What happens when you start here and f increases? What's happening? F's positive, so g prime is positive. So right out of the gate, I have a left endpoint. What happens when g prime is positive? G must have been increasing. And what happens when you increase out of an endpoint? That makes the endpoint a minimum. Do you agree? Do you agree? Local. What next? What happens when you are, what's g doing on the interval from 2.5 to 3? What's g doing? Cole?
The negative slopes are decreasing.
What's g doing?
They're flattening out.
Increasing, decreasing, or constant?
Decreasing.
G is decreasing because g prime is negative. Don't let your eyes deceive you. Is g prime negative right here? Some of you are saying no. Please focus in. Is g prime negative right here? Yes, because g prime is f, and f is negative right there. You were all looking at f prime, weren't you? You were looking at the slope of this graph. What's the slope of f? Positive. That's not what we're looking at. We're looking at g prime, which is f, and f is below the x-axis. F is negative, therefore g prime is negative. And what happens when g prime is negative? G must have been decreasing. What happens when you decrease into a right endpoint? Minimum. Question. What is the absolute minimum on G? Give me the Y value. Cool.
It's the first endpoint on x equals 0 because that's the lowest point it is. The negative from 2 to 3 doesn't negate the positive from 0 to 2.
Give me the value.
0.
The minimum value on this graph, not this graph, on the G graph is 0. How many minimums were there? Minimum, because it was a left endpoint and G increased. Minimum, because it was a right endpoint and G was decreasing into it. There were no interior minimums. Do you agree? So guess what? We have to compare these two Y values and see what's the lowest. What's the Y value to start with on the G graph? Well, what is G of 0? Well, oh, I didn't ask for it. What's G of 0? Integral from 0 to 0. Oh, 0. G of 0 is 0. What's G of 3? We're going to compare them. Pi over 2 minus a half. Well, pi over 2 is like 1.57, right? Half of pi. Minus 0.5, it's over 1. Minimum, minimum, this one's the lowest. G of 0 is the lowest. I don't know about you. This stuff is it's kind of deep. It's hard to picture because you're looking at a graph and the slopes of it, and you're looking at the area under it sometimes, and it's a lot to keep track of. Do you agree with that? All right, maybe it's just me. All right, moving on. I didn't ask it, but would you be able to identify where G has a point of inflection? Ouch. Wouldn't we look to G double prime? And G double prime equals F prime. And we want to see where G double prime changes sign. Cool.
1 and 2.5.
What's F prime? It's the slopes on this graph. Where do the slopes on this graph change sign? Positive slopes, 0 slope, negative slope. Yep. Point of inflection at 1. Negative slope, negative slope, negative slope. Oh, still negative slope, negative slope, negative slope. Positive slope. Okay. Sound effects are necessary here. All right, officially going into your notebooks, the fundamental theorem of calculus. We're going to call this part 1. The fundamental theorem of calculus. Actually, I feel bad I didn't get my wife for that.
Did she get one for you?
No.
Okay.
I think it's top of others.
It's a good idea.
What's that?
It's very handsome.
She always does
Solid.
that. You can always go with the old my presence is your presence. It's kind of very I'll go to Aldi and see what they have in the specialty item. It's our first one.
Not a culture nurse. More of a Johnny Wilbur. That's like $4.
It is
It's better experience.
experience. Do you enjoy hanging out with people over the age of 7?
It's one of my favorite pastimes.
Okay, there you go.
Lane's a bad guy. He enjoys the bags. He gets done.
Oh, definitely. They're useful.
Okay, hate the environment.
One man is here.
So instead of going green, you're going to go gray.
Yeah. That's
Pollute the atmosphere as much as you can.
with the truck. Everything.
He's gotta make sure that you're not making a difference. Save him with that. It's gotta be double.
All right, we have already discussed this in quite a bit of detail. Would you agree? We okay with it? If we're calling this, by the way, if you look up here, this name will change. In the last problem, it was called g of x. Here it's called capital F. Okay, whatever it's called, you need to understand it's the area function. Capital F here is the area under F. It's the area function, correct? How did I prove that to you? Well, I took the antiderivative, I plugged in x, I plugged in a, and I subtracted. Correct? But what happens, this is the area function, by the way, what happens when you take the derivative of that? What's the derivative of capital F of x? little f of x. What's the derivative of capital F of A? 0. It's just f of x. Back to the original. Yes? Awesome. Moving on. You don't need to write this down. Every continuous function f is the derivative of some other function. What does that mean? What are the implications of that? Watch up here. Every continuous function f is the derivative of some other function. Meaning every continuous function has an antiderivative. Okay? Every continuous function has an antiderivative. These are linked together conceptually. And these processes, as I've described them before, are inverses of one another. All right. We've done this before. I think we can skip it. Do you need more explanation? We even did that on that challenge worksheet. Awesome. Moving on. Now I want to show you what happens when the bounds change. We touched on this a little bit. Please add this to your notes. Okay? Add this to your notes. Do you remember what that 5 up there does? It's not x anymore, it's 5x. Do you remember what changes in this process? Okay, let me show you. By the way, is our answer going to be an area function? No, it's the derivative of the area function. So we're going to get back to the original, but is it just f of 5x? Maybe. We'll have to see. All right, here we go. This part. How do I write this symbolically? Capital F of... Okay, are we missing people today that are like people who speak all the time? I mean, Tony. But I miss you, Tony. He won't listen. Tyler. Bye. Oh, Logan, yeah. I miss you. All right, capital F of 5x minus capital F of pi. Blue, area function. Blue, area function. I don't know what it is. They didn't tell us what f is. But we're taking the derivative. Here we go. What's the derivative of capital F of 5x? Any brave takers? Little f of 5x times 5. I agree. Chain rule. It's not just f of x, it's f of 5x. By definition, this is a composite function now. It has 5x plugged into all of its x's, whatever it is. So when you take the derivative of it, do you agree we have to use the chain rule? What's the chain rule? The derivative of the outer function, little f. Leave the inside alone, 5x. Times the derivative of the inside, 5. Minus 0. Minus 0. Pi is a constant. Capital F of pi would be a constant. The derivative of a constant is 0. So why was this worth doing? What does 5 f of 5x tell you to do? All right, let's make this concrete. Cotangent squared 7t dt. What's my answer? Do you agree little f of t is cotangent squared of 7t? That's little f of t. We did this process for a reason. I need you guys to really listen. We did this process for a reason. I just showed you for any continuous function, little f of t. If you want to solve a problem like this, I don't care what little f of t is, as long as it's continuous. Then you take 5, okay, 5 times little f of 5x. What does that tell you to do? Take 5x and plug it in for every t. What's 7 times 5x? 35x. That's your answer. Take 5, not literally, take 5 and multiply by little f of 5x. Okay, little f of 5x is cotangent to square root of 35x times 5. Does that make sense? I told us the process. All right. What if it's the derivative from pi to 5x of, I don't know. Nope. T squared minus 2t dt. Tells us to take 5 times little f and plug in 5x for every t. Is that right? Does that make any sense? Could I check that answer? Question. Could I take the antiderivative of t squared? What would I get? 1/3 t cubed minus 2 squared plus c. Plug in 5x, plug in pi, subtract, get a function, but then you're taking the derivative of that, aren't you? This is what you would get. Does that make any sense at all? Okay. Now what if, you guys know what to do there. What if we have a problem like this that's very similar? What's different about this one? The x is on, it's the bottom bound now. Does that affect anything? There's 2 ways to approach this one. You guys have it written down? It's number 13 in the book. It's not one of your homework questions, but we'll do it anyway. All right, they're asking us to find the derivative of this thing. Option 1. Couldn't I rewrite it with a negative out front and make the bounds proper? Remember, that's a property. Switch the bounds, make the opposite out front, opposite area. So if this x were up top and we're taking the derivative of this, wouldn't it just be ln of 1 plus x squared if the x were up top? So since we switched the bounds, it's going to be negative ln 1 plus x squared. Now, another way to look at it. Isn't this part going to be capital F of blank minus capital F of blank. Help me out. If I leave it like this, is A or B? Which one's on the top? A or B? Always. B. It's supposed to be B, right? A to B. So it's going to be capital F of 6 minus capital F of x. And when you take the derivative of that, what happens? Now the 0 is the first term minus the derivative of capital F, which is little f of x. So you see how it takes care of the opposite sign there? It works its way into the algebraic process. Kind of neat how that works. All right, what's affected if we make this a 7x here? How does that change my answer? Cool.
Be negative 7 ln 1 plus 49x.
You guys agree? We take 7x, we'd square it, 49x squared. Very good. Now, what happens if we have an x squared up there? You notice they told us y. Y is the area function. Y equals the integral. Instead of a of x or b of x or c of x or whatever, it's called y. But we're taking the derivative of that function. Go ahead and try this one on your own. What'd you get? Lane, what'd you get? Nothing yet? Guess. Cole, let's see.
I said 2x times sine of x squared.
2x times the sine of x squared. Who agrees? Who disagrees? I agree. So what was that? It was, well, let's break it down again. If you ever forget, go back to the roots of it. It's capital F of x squared minus capital F of 1, correct? But we're taking the derivative of that. What's the derivative of capital F of x squared? Little f of x squared times 2x, the derivative of x squared, 2x. So take 2x out front and plug in x squared for every t in the problem. Okay, that looks right. Make sense? Last one for today, I think. Now we got 2x on the bottom bound, x squared on the top bound. That's what I got. Do you notice how this is different because neither one of the bounds are a constant, so the derivative of that part doesn't go away anymore. We have two parts to this answer. Does that make any sense at all? Please ask if you're confused. This is crazy, man. I don't know about you guys, but you know, let's spur on a little bit of conversation. Yeah, right. This is insane in the fact that what are bounds? Aren't they where you start and stop finding area? What are bounds here? 2x and x squared. They are functions of x and they're not growing at the same rate. So like you're finding area under this function. The lower bound is at a rate of 2x. The other one's at a rate of x squared. And sometimes, for fractional values like 1/2, what's happening to the bounds? What's the top bound for a half? A fourth. What's the bottom bound? 1. That's reversed. But sometimes x squared is more than 2x. It's a proper integral. Sometimes it's improper, but it works out. It works itself out. So the area function, it's pretty tough concept to grasp, but the bounds are changing at different rates, and it still works out this way. All right. All right, we're going to get into tomorrow something that's a little bit messier. I'm going to pass back. I want to make sure everybody's taking the quiz. Our homework for tonight. I can enlarge it for you. Tabs. Come on. There you are. All right. Page 302. All right. 1, 2, and 6. You're just finding the derivative of the integral. Should go pretty quickly. 14. Same thing. 23. I'm actually going to have you skip 23 right now. We didn't. That was the problem I said we're going to get to tomorrow. We're going to run out of time. So don't cross it off. Just maybe skip for now. 27. It said, here's the direction. Now, this book was published back in 2007. So I'm going to try to make sense of this to you. Evaluate each integral using part 2 of the fundamental theorem. Here's what I'm saying. Part 2, we've done it. Antiderivative. Plug in the upper bound, plug in the lower bound, subtract, get an area. Done. Okay? You're going to have to remind yourself what were these functions. To know what their antiderivatives are, you need to remember what the derivative rules were. So if you see 1 over x, what derivative did it come from? ln of x. Okay, we'll talk about absolute value there tomorrow. And so forth. Okay, trig ones, you should recognize which ones they came from. That's for 27, 31, 33, and 35. Okay? Is anyone in here still not taking the quiz? I think this class did a pretty good job of